Good day to you, dear colleagues and participants of the 8th International Conference on Energy Smart Systems. My name is Vitalii Peshko, and I would like to present you a report, Effect of Startup Operating Modes on the Cyclic Damage of Thermal Power Plant Units. The authors of this work are Olga Chernousenko, Vitalii Peshko, Dmitro Rindyuk, and Inna Bednarska. Let's talk a few words about the relevance of this research. Ensuring reliable operation of the power system requires sufficient maneuvering capacities to maintain a balance between the level of consumption and generation. Pumped storage power plants and gas turbine units are characterized by higher maneuverability. However, the energy systems of many countries around the world have an insufficient percentage of such capacities in their balance. For this reason, thermal power plant units are often involved in the peak and semi-peak part of the schedule of electrical loads. And here, for example, we can see such a schedule of daily electricity generation and consumption for power system of Ukraine. And as you can see, it's presented for October 14th, by the way, the same date as the present, but 1 year ago. As we can see, the level of generation of thermal power plants during 2 a.m. was nearly 4100 megawatts. And this level decreased to 3600 megawatts and one more time increased during evening peak to 5200 megawatts. Such work is accompanied by the deterioration of economy and environmental friendliness, deterioration of reliability and durability of our equipment. So the study of operating modes of power equipment to minimize cyclic damage is a complex and urgent task because it allows to increase the resource indicators of equipment and reduce the maintenance cost. On this slide, it's presented our main mathematical model of low cycle fatigue calculation. We're going to calculate permissible number of cycles, of startup cycles, also taking into account the creep phenomenon, as you can see. Number of cycles till destruction are calculated with the usage of experimental low cycle fatigue curves, which requires to calculate the amplitude of strain intensity with the usage of this equation. Also, we must solve the boundary value problem of thermal conductivity and calculate the stress-strain state of object of our research. By the way, the object of our research is an intermediate pressure rotor of K200 steam turbine. This rotor is made from 25 chromium steel. First 7 stages of our rotor forged together with the shaft. The other 4 stages are mounted on the rotor in a heat-shrinkable landing. As you can see, the calculation model of our rotor is set in 3-dimensional formulation, and this model is sampled by approximately 10 million finite elements. As you can see, the computational mesh is compacted in the radial direction, and especially in the zones that are stress concentrators. On this slide, we can see startup schedules for 200 megawatt power units, which are using on the real existing power units of energy system of Ukraine. These schedules are presented for startup from the cold state of metal, which means that the temperature of turbine control stage area is lower than 150 Celsius degrees. This startup is performed on the sliding parameters of steam and lasts about 10-9 hours, depending on the temperature of metal. The full startup can be set on several stages. For example, the first stage is preheating of steam pipelines and flowing part of the turbine. Then we are going to push our rotors to idle frequency, then synchronize the turbine generator with power grid, loading our turbine generator to its nominal capacity, and after reaching 200 megawatts, we are going to stabilize the temperature field of all our turbine unit. As you can see, both schedules are quite different. For example, the first preheating step lasts 33 minutes for the first unit and 33 minutes for the second one. This allows us more uniform heating of the flowing part of the second unit and perform subsequent stages of startup with the usage of steam with higher temperature and higher enthalpy. Pushing and accelerating the turbine unit on the second stage to idle frequency is faster with a less steam consumption comparing to the first schedule. And also, as you can see, the way of loading of our unit differs for both startup schedules. And only after reaching 200 megawatts electrical load, both schedules become similar. As you can see, the duration of first, second, third, and fourth step of our startup for the first unit is nearly 381 minutes, and for the second startup schedule is nearly 355 minutes. On the next step of calculation, we are going to, in accordance with the presented startup schedules, find boundary conditions of heat exchange and calculate the thermal state of our rotor. As you can see, on the operation of electric capacity of 200 megawatts, the highest temperature are observed in the area of the first control stage of turbine, and the temperature level are lowering during actual way of flowing of our steam. With the usage of this data about thermal state of rotor and other boundary conditions, we can calculate the stress-strain state, which are shown here. As you can see, the maximum values of stresses are observed in the axial opening under the control stage of the turbine. In the groove of annular crack, this zone is zoomed in on this part, and also in unloading openings of all stage disks. So the same data was observed for all operation periods of time during startup from the cold state. And this data summarized on the next slides. For example, here we can see the variation of temperature gradients. We decided to choose some study areas of our rotors, 7 areas, which are shown here. And for these areas, we can see the variation of temperature gradients, which can show us unevennesses of temperature fields. As you can see, the highest unevennesses are present during the startup period when we are pushing our rotor to its idle frequency. And these temperature unevennesses are shown for both schedule of startup. The maximum values of temperature gradients are nearly 4,000 Celsius, 4,000 Kelvin degrees per meter, as you can see for both schedules. And these high temperature gradients are observed in areas 5 and 6, which corresponds to the first control stage of turbine rotor. For the rest studied areas, there is a significantly lower level of temperature gradients, as well as less significant fluctuations of these values, which you can see on further periods of time. The same data was observed for stress intensity, and as you can see for the same areas, there is shown stress intensity. As you can see, the highest tensile forces are observed in the first area, which are axial opening under the control stage. As you can see, for both startup schedules, the highest value is nearly 310 megapascals. But for the second startup schedule, the period of time in which we can observe these high stresses are much lower than for the first startup schedule. And same thing with the compressive forces. As you can see, for the areas 3, 4, 5, and 6, the highest stresses are compressive. And compressive stresses above the 400 megapascals are observed for much longer period of time of first unit comparing to the second one. So all this data was summarized and used for calculation of indicators of accumulation of low cycle fatigue in our turbine rotor. These indicators are presented on the table on this slide. As you can see, elastic modulus and tensile strengths are indicators which are temperature dependent. All other indicators are calculated. For calculation of amplitude of strain intensity, the normative margins of safety were taken into account. These margins are described in some regulatory documents, and permissible number of startup cycles calculated with the usage of experimental low cycle fatigue of our steel 25 chromium. As you can see, the permissible number of startup cycles for the first unit is nearly 33 launches, and for the second unit is nearly 3,800 launches. So due to the more uniform heating of our turbine and during a more rational startup time, it was possible to increase the permissible number of cycles nearly 16%. And since the 200 megawatt power unit launched about 1,500–2,500 times during its life cycle, the obtained values of the allowable number of cycles are satisfactory for our equipment. But we should note that the accumulation of low cycle fatigue is not the only mechanism for damaging of steam turbine equipment, but it's one of the main damaging factors. So our study showed that the improving startup schedules can significantly increase the durability of power equipment. Development of special schedules that minimize the accumulation of low cycle fatigue is an important research area. It is recommended to pay additional attention to the efficiency of power plant and the complexity of its implementation of our startup schedule for the operating personnel. Because as we can see, the second startup schedule allows us to get more permissible number of startup cycles, but it's really a bit harder for implementation for operating personnel on the power plant. The second schedule is harder. So let's highlight some conclusions of our research. As we see, startup of the turbine equipment of the power plant is a complex and responsible mode of the operation. It's characterized by significant damage of the metal by the mechanism of low cycle fatigue. To assess this effect of damage of our startup operating modes, we are consider two different startup schedules. These schedules are used on the existing 200 megawatt power units of energy system of Ukraine. They are differs in the parameters of the steam and the duration of some startup stages. Based on the study of thermal and stress strain state of the rotor during startup, it was found that the greatest non-uniformity of temperature fields occurs during push of the rotors. At the same time, high stress intensities are observed later for the period of time from the running on the idle frequency to the loading of 30 megawatts of electric power. The amplitude of stress intensity in the cycle is nearly 260 megapascals for the first schedule and nearly 240 megapascals for the second one. It is calculated that the permissible number of startup cycles for both units with the help of experimental data on low cycle fatigue of 25 chromium steel is nearly 3,300 launches for the first unit and 3,800 launches for the second unit. Due to the more uniform heating of the flowing part of our turbine and more rational startup time, it was possible to increase the permissible number of cycles for the second unit by nearly 16%. That's all. Thank you for your time and thank you for your attention.